Okay, so chapter 36 is about diffraction. So in this chapter, we're going to learn how light is diffracted by a single slit, and you're also going to learn how the intensity would be when you have a double slit interference pattern, and also diffraction by a circular aperture, and also diffraction gradients and X-ray diffraction. Okay, so let's start with the single slit. So previously we learned in chapter 35, we learned, when you have light sent through a double slit, it's going to produce an interference pattern, and the intensity will be very regularly, spaced, regularly spaced, and roughly they have this equal intensity. So that is the intensity pattern produced by a double slit interference experiment. What about when you use a single slit instead of a double slit? So when you have a single slit, single slit, and when you send light through the single slit, what we found is that it's going to produce what we call the diffraction pattern, and the intensity distribution is different from the intensity produced by double slit. And so let's look at how the intensity will be different. Previously we mentioned that when the width of the opening is comparable to the wavelength of light, then diffraction can occur. Okay, so last chapter we talked about double slit, and the intensity are regular. They have equal amount of intensity, and that is because the width is much smaller than the wavelength. So that's why you don't really see the variations in intensity. However, when you're dealing with a single slit, when the single slit the width A is comparable to wavelength, you'll find that the intensity will be different on the screen. So let's look at how the light ray interfere with each other when light was sent through a single slit. So this is a slit slit width A, and that's say in order to determine the path length difference, we can actually, and this is the central axis, we can actually just think of this this slit as two slits, and each each slit has the width of a over 2, half the width. So then we can compare the light ray that's traveled from this point to that point, and then the light ray from this point to that point, and see how much additional distance that is traveled by ray 2. So when you do that, you can see that we're using exactly the same procedure as for the double slit interference experiment. So this has a over 2, that is your hypotenuse, and this angle is the same as that angle, theta here. So comparing R1 and R2, you can see that this is the additional distance that is traveled by R2. And so this distance, is equal to A over 2 times sine theta. Okay, so this is the path length difference between R1 and R2. Now, and then we're going to set it equal to half a wavelength, because we want to find the location for the dark fringe. Okay, so you're going to see that for a single slit, the intensity pattern will actually behave like this. So let's say this is a central bright fringe, and then you have the another bright fringe, and another bright fringe. And you can see that the bright fringe will actually have a spatial extent, and the dark fringe will probably just the dark fringe will just be like a point. So in other words, the location of the dark fringe is a quantity that is much easier to identify. For the bright fringe, it actually had covered a substantial extent in space, so you can't really it will be difficult to actually decide the locations of the bright fringe. But for the dark fringe, it will be just like one dot with a much narrower extent. So when we find the path length difference, instead of setting it equal to lambda, we are setting it equal to half a wavelength, because our goal is to find where the minimum is located. So when you do this, so when you have a over 2 times sine theta, that's equal to lambda over 2, we find that these two cancel. So the first minimum will occur when a sine theta that's equal to lambda. Okay, and that's what this equation tells you. So you have the a and times sine theta, that gives you, that's equal to 1 lambda. This is, so the theta there will give you the locations of the first minimum. Okay, and then, so what about higher orders? So we can also do that. That's continue to divide the this top half into draw a lot of line to from the midpoint at this point. And so when you do that, this is equivalent. So this is like this. So this is the middle. So this is the total width A, and then we cut it in half, and then we're going to further cut it in half, and then we're going to compare the path length difference between R1, this one, and R2. So when you do the R1 and R2, you can see that when you do the R1 and R2, this is basically like this. So this, instead of A over 2, now this hypotenuse becomes A over 4. And then the additional distance is still this, and this is theta. That's your theta. So in other words, the additional distance that ray 2 has traveled will be a quarter of the width times sine theta, and that's equal to lambda over 2. Again, we're finding the minimum, and that will be our second minimum. So in that case, your a times sine theta, that's equal to 2 lambda. That is your second minimum. So if you continue to do that, further divide into half, and then further divide into half, you'll find that in general the condition for dark fringe is this equation, which is a sine theta is equal to m lambda, and your m starts from 1, 2, 3. So in other words, that tells you the locations where the dark fringes occur. So when m equal to 1, we write down a sine theta 1, that's equal to 1 lambda. And from there, you can calculate what the theta 1 is. Okay, and then when m equal to 2, then you would say a times sine of theta 2, that's equal to 2 lambda. And then when that's 3, and then 3, and then 3. So in other words, this, when you change your m value, you're going to change the angle. So this is like, for example, this is m equal to 1, m equal to 2, n equal to 3. And so you can see that this help you identify where the minimum occur. Okay, and it's symmetrical about the central axis. So you expect m1, m2, and m3. Okay. So we can see that for double slit, we're saying that d sine theta, we're setting d sine theta that is equal to m lambda, and that's for bright fringe. But when you're dealing with a single, single slit diffraction pattern, we're using this equation. That's a sine theta, that's equal to m lambda, and that's for dark fringe. Okay, so that's the difference between the double slit and single slit. One is looking for the locations of bright fringes, and the other one is looking for the locations of the dark fringes. And that's that. So let's look at the diffraction pattern. As I mentioned, for diffraction pattern, it's different from the interference pattern by the double slit, because the diffraction pattern by a single slit, actually will produce intensity pattern like this. So it just imagine that this is a screen. This is where the screen is, and this is the intensity pattern produced by a single slit. And if we look at this. This is when A, the slit width is equal to 1 wavelength. You can see that it has a much broader extent. But then when A is equal to 5 lambda, you begin to see that it has some structure, and the central width, this central width is actually smaller. Instead of a broad range, it actually gets smaller when A is larger. And when A is even larger, let's say it's equal to 10 wavelength, you see that, this becomes even narrower than the previous one. In addition to that, you see more structures. So this basically, has the, this is basically the typical pattern for diffraction pattern. So shining on the screen, this, like I said, this is a screen. And so I think what you will see when A is equal to lambda, you'll probably see a bright fringe like this. And then for this one, you'll see a bright fringe, and then another bright. And then for this one, you will see bright fringe, and then here, and then here. Okay, so you can see that the intensity pattern, the intensity extent gets narrower when A is larger. So, and also based on this, you can see that this is your M equal to 1, M equal to 1. This is where the dark fringe occur. Okay. And then this is the, so this is M equal to 1, dark fringe, M equal to 2, dark fringe, and M equal to 3, dark fringe. Okay. All right, so that's why, for the single slit, we're looking for the location of that fringe because it's easier to find. Okay, what about this? The intensity. So the intensity for diffraction pattern, we use this expression. So it is, the intensity is a function of angle. The horizontal is the angle. Is a function of the angle, and you have the central maximum. So IM indicate the intensity as central maximum. Okay, and then times sine alpha over alpha square. Okay, so what is alpha? Alpha, the quantity is this. Is pi times the slit width over the lambda, and then times sine theta. So that's why intensity is a function of angle because alpha itself is a function of angle. So you can see that, let's say if you are, let's say at this location, what is the intensity at that location? You would do this, okay? So how do we do that? We know if we know the maximum intensity, that's that value, and then we need to figure out what is alpha. Alpha is pi a over lambda times sine theta. And this is the angle. If you know the angle, and then you can plug into this, and then you can calculate your alpha. Okay. So from there, you plug into this equation that will help. That will get you the intensity at this location. Okay, so that is the intensity, how you calculate the intensity on this diffraction pattern. Now, here you have to be a little bit careful when you calculate alpha. This will give you, a numerical value that's in radians. And so when you substitute the numbers into this equation to calculate the intensity, you want to make sure that, this is in radians. You still have to use radians. Now, what about the sine alpha? So in this case, it depends on the setting on your calculator. And I think most of the students, they will have it set it in degrees. So if that's the case, you have to convert your alpha in radians to alpha in degrees and then plug in the degrees in order to do the calculation. Otherwise, you're going to get a wrong number. Okay. So when you apply this equation, when you use this equation, just be mindful that, what is the setting on your calculator? If that's in radians, that's fine. You don't have to do anything. Just plug in the radians and calculate sine alpha. If the setting is in degrees, then you want to make sure that you convert your alpha into degrees, and then do the sine alpha. Now, in a denominator, you still you want to use the in radians. Okay. All right. So this just tells you that how intensity changes as a function of the angle. The farther away, of course, we know that it's going to get smaller just based on this diagram, and also from this you can see. Okay. All right. And so this basically that just a proof. We're just going to skip that, and then diffraction. So the diffraction pattern that we saw, is for a single slit that is kind of rectangular shape. You could have a diffraction pattern that's produced by a circular shape. For example, a lens, right? So when you have a lens, and then when the light passes through a lens itself can be considered by light as the obstacle. So when light passes through a lens, it's going to be diffracted. And so the width of the lens, which is the diameter, will be the opening of the slit. Okay, so the diffraction pattern produced by a circular aperture will not be what we saw earlier, that is a dot. It's actually circular. So you can see that the diffraction pattern produced by a circular aperture will produce a pattern like this. So you have the central maximum, and then you have the first order maximum and the second order maximum. And you can see that the intensity get dimmer progressively when it's farther away from the central axis. And in addition to that, you can identify this is your the first minimum, and this is your the second order minimum, third order minimum, and so forth. And the width of the minimum actually gets larger when it's farther away, and the brightness at the thickness of the brightness actually get thinner when it's farther away. Okay, so you can see it's kind of interesting. So for circular aperture, the first minimum of the diffraction pattern occurs. So we're talking about the first minimum. So this is the location. So where does the first minimum occur? It occurs when sine theta, that's equal to 1.22 times lambda over the diameter of the aperture. Okay, and we only provide this expression for the first minimum because for circular aperture the derivation is actually quite complicated, and high order location, the expression is a little bit difficult, complicated. So we're only providing you with this information that is for the first minimum. Okay, where would the first minimum be located? That it will be located when sine theta is equal to 1.22 times lambda over d. Okay, so again, if I draw axis like this, horizontal, a straight line horizontal. It's kind of difficult to when I draw in mouse, use the mouse. Okay, and so and then this is the zero, center. So that's your 0 degrees there, and then so this is your theta. Okay, so whatever theta that is, this theta is equal to, how to calculate that, is 1.22 lambda over d, and d is the diameter of the aperture. Okay, so then when light passing through a circular aperture, it's going to produce a diffraction pattern, and so when you have a distant object and when you want to use the let's say telescope to observe distant stars, sometimes depending on the how resolving power of your telescope, you may not be able to resolve two objects if they are located so far away. So you need to have a very high resolving power telescope in order to discern two objects when they are located far away. So in order to discern object that's located far away, the telescope or any aperture device has to satisfy this criterion. So what is the radius criterion? So radius criterion for resolvability would be that the central maximum, which is this, the central maximum of the diffraction pattern of one source is centered on the first minimum of the diffraction pattern of the other. So let's say you have the two objects. So these two objects, let's say you have two objects. Each object is acting as a light source. So the object is going to, when you use a telescope to observe these two objects, each object is going to, has sent through, what emit light source, will emit light rays, and that light ray is going to pass in through, the telescope. So this one, the source one is going to produce a diffraction pattern, and source two is also going to produce a diffraction pattern. So in order for the telescope or the lens to discern that they are actually two objects, then the criteria will be that the central, the central maximum of the first diffraction pattern will be located at the will be, it should be centered on the first minimum of the diffraction pattern of the other. Okay, so in other words, when you have the one, so this, oops, so the other object is that is located like this. This is the central maximum of the produced by a second source. Then then it is on the first minimum of the first diffraction pattern of the first light source. So you can see that you can actually discern that it's actually made of the two objects. So in other words, if the two central maximum, if the central maximum of this one and that one, they are so close to each other, you can't really discern that they are actually two objects because they are too close to each other. Now, if the central the central maximum of the second one is located at the second at the first minimum of the first one, then you start to see that it seems to be of two objects. Now, if they are well separated, this is like, this has this diffraction pattern. This is the central maximum of first one. This is the central maximum of the second one. And if they are well separated, you can see that, okay, it is, when you use a telescope to observe this, you know that they are actually you're observing two stars instead of one star. Okay, so in other words, when you're using a low resolving power of a telescope, if you see a big blob, like this, you might it might appear to be just one object. But if you're using a higher power, higher resolving power telescope, then you actually see that it is actually two stars. Okay, so the condition for the lens for the circular aperture to be able to resolve the diffraction pattern would be that it has to satisfy Rayleigh's criterion for resolvability. And so what is the Rayleigh's criterion for resolvability? That would be when theta r is equal to inverse sine 1.22 lambda over d, and you can see that it's actually just like this equation, but we just take the inverse sine, and this is the minimum angular separation of these two. So this is the angular separation. The minimum angular separation has to be equal to the Rayleigh's criterion, Rayleigh's angle, in order for it to be barely resolved. So this is like when it is barely resolved. Now, if your theta, the angular extent of the separation is is greater than theta r, then you can see that it is you can resolve the objects. Okay, so the minimum requirement for the circular aperture to resolve two objects would be that the angular separation of these two objects has to be equal or greater than the Rayleigh's criterion in order for the objects to be resolved. Okay, and so the Rayleigh's criterion is 1.22 times lambda over d. Okay. And so the next thing we want to talk about is that, what we have we mentioned that when you have a single slit, we want to use A sine theta that's equal to M lambda to find the locations of dark fringes. And in chapter 35, we learned that when you have a double slit, then you want to use D sine theta that's equal to M lambda to find the locations of bright fringes. So let's imagine that now you have a double slit. You have a double slit, double slit, but then so it has the slip width, slip separation, that's D, but then the slip width itself has A, and let's say that for that double slit, your A is comparable to the wavelength. Then when you have light, when you send light through the double slit, it will have the interference pattern produced by the double slit, but embedded in that intensity interference pattern, you should also expect there's a diffraction pattern produced by the single slit because now your A is comparable to the wavelength. So in other words, you have this, this is when you have the intensity pattern that is produced by the interference. And so then you can see that when the slit width is much less than wavelength, you can see that vertical is the intensity and horizontal is the angle. You can see that at each point on this space, it produces the intensity that has the same amount, and it's very evenly spaced throughout throughout the screen. So on the screen you would expect to see something like, okay, dot here, dot. This is very difficult to draw using mouse, but you get the idea. So you have the dot, 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 and so you see a lot of bright bright dots on the screen. But then for the intensity for the single slit diffraction pattern, when A is comparable to wavelength, you would expect that it produce the envelope like this, right? You have the big giant bright region, and then you have the smaller one, and then you have the first minimum like this. Okay, so what about when you have a double slit that when A is comparable to the wavelength, then you should this will become that you have to merge this two. So when you merge this two, and then let me draw the the envelope here. So you have the envelope like this and like this and like this. What you found is that everything outside this envelope will not be permitted, will be gone. So the only thing that left is inside the envelope. So in other words, when you merge these two patterns together, all this are filtered out. The only thing that will remain will be inside the envelope. Okay, so this is basically this figure shows you the realistic pattern produced by a double slit, because for a double slit, most likely your the width will be comparable to the wavelength. So you should expect that diffraction pattern will also be shown in this intensity pattern. So you can see that inside this big envelope, they are bright fringes. Okay, there are bright fringes and there are dark regions as well. Okay, and then inside this big envelope, so the single diffraction pattern determine this big envelope, and inside this diffraction pattern, the bright fringes are determined by the double slit. So for the big envelope, you will use A sine theta that's equal to m lambda to determine the location of dark fringes. You're going to use D sine theta that's equal to m lambda to determine the locations of bright fringes inside the envelope. Okay, what about the intensity? So for intensity, for a double slit, then this is the equation to use. Okay, so the intensity is equal to the central maximum intensity times cosine beta square, and then times sine alpha over alpha square. Now remember, previously when you only have a single slit, where we said that intensity is equal to Im sine alpha over alpha square. But then when you consider double slit, you also have to consider the interference pattern. So when you merge them together, which means that you multiply them together, then this is the intensity expression. So you have you have this equation, and then alpha, we still use that same is pi a over lambda sine theta. What about your beta? Your beta is pi d over lambda times sine theta. So you can see that this refers to the double slit effect because it has the slit separation, and this is for the single slit because it has the slit width. The sine theta is what relates the single slit and double slit, because at the at certain location, let's say at this location, the angle theta, you will have the sine theta. So that same theta will be the same for for both in both equations. Okay, so so this is the equation that you will use in order to calculate the intensity, let's say of this one. So let's say this is actually the m equal to 1 for the double slit. intensity. So m equals 1, the 0th order, and this is of course the first order, second order, third, fourth, and so forth. And it's symmetrical about the central axis. So this is also m equals to 1, m equals to 2, n equals to 3. So don't get confused about the same m, because the m that I'm talking about here, that is the m, for the bright fringes. And for the single slit, the m I'm talking about is refers to the order for the dark fringes. Okay. All right. So so again, again, when you calculate alpha and beta, you're going to get those in radians. And so when you plug into these equations, you want to make sure that it is in degrees if your calculator is set in degrees. Okay. Alrighty. So the next thing I want to talk about is that, we use diffraction. Diffraction, has a lot of applications. And one of the applications is is we use a diffraction gratings to determine wavelength of the light source. And the concept behind that is that, let's say you have a light source and then produce a wavelength lambda, and then you send a light ray passing through gratings. So instead of one single slit, instead of a double slit, we now have a lot of slits. So you can see that all this cutting are actual slits, and the light is going to pass through each one of the slits, and then they are going to interfere with each other. When they interfere with each other, then they can produce the diffraction patterns or the intensity pattern. And then we're going to use, after you do the path length difference, we found that d sine theta that's equal to m lambda, and this is for the maximum light, which means that we'll use this equation to find the bright fringes on the screen. So you can see that the diffraction pattern, the intensity pattern produced by the diffraction gradient is like this. So you have the m equals m equals 0, 1, 2, 3, which is the 0th order, the first order, second order, and third order, and things like that. Okay, and the equation that governs this is d sine theta that is equal to m lambda. Okay, and now and so so these are the equation to find the bright fringes. So so the bottom one is actually when you send light, and this is basically what you see the vertical lines on the screen. Okay, so so this equation is familiar because it's actually the same as the double slit. The only difference is the d. D is the slit separation. And so actually it is the same, but then D now, how do we calculate D? Because D is a slit separation. We know, if we know the dimensions, let's say if we know the width, let's go W, and we know how many cuts on this surface, is that's called N, or number of rulings. Then this is how you calculate the spacing between this is the spacing D. How to calculate spacing between the slits? That will be the total width over the number of rulings, and then you can calculate your D. So you'll find that your D is actually a very small number, and that is because that's because for very small total width, we actually have 1,000 lines cutting to the surface, and then in order to produce a well-defined intensity pattern, when you do that, of course you want to make sure that all this all these bright fringes are far away that you can discern them. If they are too close, then that kind of defeat the purpose, because you won't be able to determine the wavelength with high precision. So you want to make sure that you have the the brightness that is produced that has a well discernible spacing, so that distance, so that you can easily figure out, okay, so this is my theta 1, this is my theta 2, and then by applying this equation, you'll be able to figure out what the wavelength is. Okay. And so that's one application for the when we use diffraction. And And then so this, this, refers to what I just briefly mentioned. We want the, the intensity pattern, for each brightness, they are well separated from the other so that you can resolve it. And so, so we're not going to go over that. And also the, resolving power, again, we're just not going to talk about that. So the final thing I want to say about diffraction is or the applications of diffraction is the X-ray diffraction. Now, previously we use lights, to produce the diffraction pattern. And what about if we are using electromagnetic wave that is not light, for example, X-ray. Now, X-ray, is a short wavelength, meaning that it's has a higher energy. It has very high energy, high frequency, so the wavelength is short. So if the wavelength is short, then when you use the X-ray, and then I just send the X-ray through the spacing like the camera, you won't be able to produce a diffraction pattern, because in order for the diffraction pattern to occur, the wavelength has to be comparable to the opening. Now, if your wavelength is much less than the opening, you will not be able to produce a diffraction pattern. So Bragg was one of the scientists was thinking, okay, so diffraction is the phenomena of wave. So X-ray is a wave. So so we can actually use X-ray to probe the atomic the atomic structure, provided that because provided that the spacing, the dimensions of the obstacle is comparable to the X-ray. So X-ray has a very short wavelength, and the atomic spacing also has a very is also very short, and they are comparable to each other. So we can use X-ray to actually probe the structure, the atomic structure, especially for crystalline structure like table salt. It consists of it is MaCl. So you have the sodium, you have the sodium ion, you have the chlorine iron, and they are regularly spaced structure like this. So you have a very well structured design, three-dimensional lattice design. So you can consider this as it's like a grating that consists of a sodium ion, chlorine ion, sodium, chlorine, sodium, and so forth. So this is like they have a spacing, and when you send X-ray through onto shine on this object, then of this material, then X-ray, then this is like a natural three-dimensional grating will produce a diffraction pattern. And then from the diffraction pattern, we will be able to determine the interplanar spacing of this molecular, the atomic structure. So conceptually, this is basically how it is. Let's say this is the top plane, second plane, and third plane, and then you have the X-ray that will send and shine and send through the MaCl, and then it's going to come to the first plane, and then being reflected, come into and reflected. So ultimate goal is that we want to find the path length difference, and if there's any path length difference, then we can determine whether the interference is constructive or destructive. Okay, so this is the so this diagram we can translate into here to help us better understand how to find the path length difference. So you have ray, you have the ray 1 here, you have the ray 2 there. So ray 1, when it when it encounters the surface, is going to be reflected. Ray 2, when it encounters the lower surface, lower plane, is going to be reflected. So ray 1 would just be going this in and out, and this is going in and out. So we can compare we can compare the path length difference between ray 1 and ray 2 to determine the path length difference. So you can just see that the red, the orange color indicate they have the same, they travel the same distance. And ray 2 has the additional distance that it has to travel, okay? And that's shown in green. So we can see that if this is the angle theta, that is in reference to the plane, and then this is theta, this is also theta, and this theta, this is theta, that is theta, so this theta must be equal to that theta. So in that case, we can, and this is hypotenuse, so this is your D. This D is the interplanar spacing. This is like the grating, the slit, slit separation. So then, so you have the, so this is your D, and then this is theta. So you have, and so this distance will be D sine theta. And because, it goes from here and there, so it's 2D sine theta. So you have a 2D sine theta. If that's equal to m lambda, then we know that it's going to produce a constructive interference. And so you have the 2D sine theta that's equal to m lambda. That's for the intensity maximum for X-ray diffraction. And your m, we don't have the 0th order. It starts with the first order. So you have the 1, 2, 3, and those integer. Okay. So the other thing I want to mention is that we talk about reflection, and the angle here is defined in reference to the plane, not in reference to the normal. In chapter 33, we talk about light incident, and the angle is in reference to the normal. But when it comes to X-ray diffraction, the angle is actually in reference to the plane. Okay, so you have the 2D sine theta that is equal to m lambda, and this is what we call the Bragg's law, and that's a criterion for intensity maximum for X-ray diffraction. So you say, okay, so we can apply this equation to determine the interplanar spacing. What does that tell us about the atomic structure? Because another diagram that help you better understand how the D in relation to the atomic structure, you can see that the NMS molecular structure, the compound structure. Anyway, so so you can see that all these are plane, the interplanar space, and the D is the interplanar spacing, and you have the chlorine ion, you have the sodium ion, and then they are equally spaced like this. So this. And so you can see that the distance between sodium ion and chlorine ion is let's say A0. That's the separation between those two ions. And then from this diagram, we see that from the red dots to red dot is actually two times the A0. And then just based on this diagram, you can see that how many planes are there. That's 1, 2, 3, 4, 5. So that's your phi D. So you can see that your phi D is equal to, use Pythagorean theorem, you can easily deduce that your phi D is equal to square root of 5 times A0. So your D here is just the spacing between those two ions over square root of 5. So once you know your D, then you'll be able to determine what your A0 is, and then that will help you reconstruct how this MaCl is structured. So the assumption is that they are regular space in and they have a three-dimensional very regular lattice structure, and so that you can do this calculation. Okay, so that's one neat applications when you for the X-ray diffraction. Okay, so this concludes the chapter 36.